Everyone. Today we're going to talk about what happens when two sound waves interfere with one another. And this is something that we get happening a lot in performance venues, specifically if you've got a space that is kind of big and empty and you've just got two speakers. So let's go ahead and take a look at that setup. All right. So essentially what we're looking at here is that we have one speaker right here, speaker one, and one speaker right here. We'll call this speaker two. And as you can see, each of them is playing a sound wave. And so these solid lines are going to be the peaks of each. And then the dotted lines are going to be the troughs or valleys. And so as we think about this, we're going to end up having both constructive interference and destructive interference happening in this room. So constructive interference is going to happen when you have either two peaks or two troughs in the same place at the same time. And that's going to create a loud sound. But if you have a peak and a trough in the same place at the same time, they're going to cancel each other out, like we talked about um, in our wave properties video. And so that is going to be a quiet spot. And so that's where we're going to start here. And for the record, if you do this experiment, you play two sounds from the speakers and you walk around, you will notice exactly what I just said, which is that there are spots where it's very loud. But there are also spots where it's very quiet. And this is actually a pretty big problem, right? Because if you're looking at a performance venue, you kind of want every person to have the same experience. You want to have them hearing the same sounds at the same levels. And if they're not, then that should concern you. Um, and in fact, that study of creating the best quality sounds we can for people is called acoustics. So I've gone ahead and drawn in all of the loud and quiet spots that we see here. And what we notice is that there's a pattern. And the pattern is as follows. Here in the middle, we have a line of all loud spots. Now, we can call this a couple different things, but one of the things we'll call it is the central antinode line. Remember when we talked about waves, we said the antinodes are like the highs and lows, right? So this is called the central antinode line because it is a really high, loud place. And basically anywhere you are along that line, it's going to be loud. But right next to it, on both sides, we have lines of quiet spots. And then right next to those quiet spots, we have another line of loud spots. And this goes back and forth over and over for as long as they're both there. So in fact, I'm going to go a little overboard here, but there are quite a few over here and over here. All right, I'm going to skip the rest. This pattern of alternating loud, quiet, loud, quiet, loud, quiet lines is called a two-source interference pattern. And in fact, later in this unit, we'll actually talk about the fact that we see this not just with sound waves, where it's loud and quiet, we see it with a lot of other waves. You can actually see this with water waves. If you get cross waters, you get a very choppy, weird square pattern that is two-source interference. But also with light. And in that case, you end up with bands of light and dark, light and dark, light and dark. But scientists noticed something when they started looking at these lines, and that is that you can actually use these lines to find out the wavelength of the wave you're dealing with. So we're going to start by numbering these lines, and we have a very specific way of numbering them. The central antinode line is line 0. And then every loud line is a whole number. So 0, 1, 2, and it just mirrors on the other side. 0, 1, 2. Now, the quiet lines are halfway in between the loud lines, so we're going to name them with half numbers. 0.5, 1.5, 0.5, 1.5. All right. So we've got this completely drawn out. And then scientists started taking some measurements. So I'm going to have up here a little table for us. And in this table, we're going to list a couple things. We're going to list the distance to speaker 1, and we're going to do this in wavelengths right now. Now, in my class, we do this as a lab, and we actually get out a ruler and start measuring. For now, let's look at it just in wavelengths. D2, also in wavelengths. And what line number we're on. So I'm going to pick a couple of points for us. Let's pick this one, this one, this one, this one, and this one. Throw in one more quiet. All right, I'm going to work these left to right. Okay, so if I'm looking at this point right here, I'm going to count how many wavelengths I am away from speaker 1. And what I'm really doing is just counting 1 wave, 2 waves, 3 waves, 4 waves. So I am 4 wavelengths away from speaker 1. We can do the same over here. I am 1, 2, 3, 4, 5, 6 wavelengths from speaker 2. And I am on line number 2. All right, we're going to keep going through these. I'm going to go a little quicker. All right, we've got 1, 2, 3, 4.5 wavelengths from speaker 1. And 1, 2, 3, 4, 5 wavelengths from speaker 2. And I am on line 0.5. All right, here, 1, 2, 3, 4, 5.5 from speaker 1. 1, 2, 3, 4, 5.5 from speaker 2. And I'm on line number 0. All right, we're halfway through. We'll go to this quiet one right here. 1, 2, 3, 4, 5, 6 wavelengths from speaker 1, and 1, 2, 3, 4, 5.5 wavelengths from speaker 2. Difficulties. There we go. And we are on line 0.5. All right, last two. We're gonna go for this one. 1, 2, 3, 4, 5.5 from speaker 1. 1, 2, 3, 4.5 from speaker 2. So 5.5 from speaker 1, 4.5 from speaker 2, and that is on line number 1. And then finally, that last one over here on line 2, we are 1, 2, 3, 4, 5, 6 wavelengths from speaker 1, and 1, 2, 3, 4 wavelengths from speaker 2. We are on line 2. So some of you might already be seeing a pattern emerging, because if we look, the difference between these two numbers, 4 wavelengths, 6 wavelengths, right? So the difference is 2 wavelengths. Oh, we're on line 2. Here, 5 wavelengths, 5.5 wavelengths, 5.5 wavelengths. There's no difference between those. Oh, line 0. 5.5 wavelengths and 4.5 wavelengths. The difference, 1 wavelength. So we notice that there's this relationship between the difference between the distances to the speakers and the line number we're on. And we're going to write that as the following. The absolute value of D1 minus D2 is n numbers of wavelengths. And what's cool is if I'm not counting this in wavelengths, let's say I'm getting out my ruler and doing the measurements, right? This still works, right? So if it's, let's say I'm on line 2, and my distance to speaker 1 is 5 meters, and my distance to speaker 2 is 1.5 meters. Then I could actually use this to figure out what the wavelength of my sound, in this case, is. And so I would do the absolute value of 5 minus 1.5 equals 2 wavelengths. 5 minus 1.5, that's 3.5, equals 2 wavelengths. And so our wavelength is 1.75 meters. These patterns show up in everything that has wave behaviors, and we can use, again, the distances to calculate the wavelength of that thing, and it's pretty cool. So thank you so much. Have a great day. Bye.